we'll start this title as the study of chemical reactions. Okay, the essence of TuTh is the study of chemical reactions. And going through this, I think you'll begin to see why I start with the concepts that are in solution phase reactions, because we'll be using molarity and moles extensively as we go through this. So when we study chemical reactions, there's three primary big picture topics when you study these. It's based upon chemical kinetics, chemical equilibrium, and chemical thermodynamics. In chemical kinetics, if you're studying this topic, we're dealing with rates of reaction or speed of reaction. And the equilibrium region of a reactive process, we're talking about studying the character of the reaction at its extent of reaction. The extent of reaction is the point at which it transitions from the kinetic region, and I'll show you in a moment, into the steady state region where the slopes of the concentration curves become zero. Thermodynamics deals with the feasibility of a process. Well, its base definition is the study of energy changes in the chemical physical process, but its application is feasibility. Of reaction process, I should say, because they're physical reactions. Now, each of these have several chapters associated with them. Chemical kinetics is the first chapter. It has its own set of rules and regulations. Then equilibrium has 4 chapters associated with it as it applies to gas phase reactions, solution phase, and precipitation reactions and the like. Thermodynamics has an entire, well, actually 2 in this text, and they're split. Chem 1, we look at thermochemistry is the title of the chapter, but it is based on first law of thermodynamics, and then we add that to the chapter on thermodynamics, and we find it, we're looking at the second law of thermodynamics along with third and fourth. But at any rate, this is our objective now, and we want to move into how these are related. Looking at this graph, and consider the hypothetical reactants going to products. We want to draw some conclusions about the behavior of that reaction. Now, the way I want you to think of this is like a horse race. And at a point in time, the reaction has not started. That is 0 point. And the horses are all in the starting gate. Then mentally you open the gate and allow the reaction to proceed or the horses to run. In doing so, it's a logical deduction that the concentrations of the reactants will go down, and of course, as the products are from the reactants, they will go up in concentration. So at the outset of the reactions to products, we have 100% reactants and 0% concentration in that context of products. Then we open the gates and let the reaction run, and it's a logical deduction that the concentration of the reactants will begin to decrease systematically and smoothly in a parabolic fashion like that, while the product concentrations from the reactants will increase as shown. Like that. Now in this diagram, there is a point in here where the slope of the concentration time curve becomes 0. As you can see, it levels out. And that point separates the kinetic region from the equilibrium regions. I'll move time way out here then, so we have space to write. In the space between 0 and the point at which the slopes go to 0, this is called the kinetic region. And the principles of chemical kinetics are applied to the behavior of reactions in this particular region. In the region where the slope of the line becomes 0, this is the equilibrium region. And in that space, we apply principles that define the reaction in the equilibrium condition, a steady state condition. Here we're in what is referred to as a dynamic equilibrium. In which we find that there is no apparent visible change in concentration of the reactants and product. However, the reaction continues in that there are reactions proceeding forward at the same rate that a reaction is proceeding in the reverse direction. So this is what we call the law of mass action. And so in the equilibrium region, and we'll develop it in more detail when we get there, this is based upon the law of mass action. And is rate forward equals rate reverse. And that's as far as I'm going to take you at this moment in that region of the study. But I wanted to show you how it is evolving from the kinetic side of the curve. In the kinetic region over here, the issue is how fast is the reaction proceeding. So the principles that we're studying in this region all focus on speed of the reaction, rates of reaction. And that involves, it's much like the speedometer reading on your automobile, a change in distance over time. Well, in chemistry, we measure changes in concentration as a function of time as the reaction proceeds from start to wherever it's going. And we have change in concentration over change in time as the core definition from which we build all of the principles and applications that go into studying the rates of reaction. In the scientific community, people will spend their entire lives just studying, say, kinetics of some chemical process. There are those who specialize in the kinetics of enzyme behavior, protein behavior in a very small window of chemistry, whereas some people spend their lives working over in the equilibrium region and studying the principles and applying those principles. But my job, of course, is to give you a taste of both sides of the equation here, equilibrium and kinetics. So we will start developing this. The other issue in the study of chemical reactions is thermodynamics, and I'm just going to make a note over here. And as mentioned, thermodynamics is purpose is to define feasibility of reaction process, meaning that if we apply certain principles in thermodynamics, we can determine, yes, this reaction will proceed to products under the conditions that are specified, or no, it will not. And it is a thermodynamic transition point, and you'll learn in this section how to take a reaction and define the exact conditions that will make that reaction proceed to products. It's kind of like a ball rolling downhill. If it's at the bottom of the hill, it's not going to react, but you can move it up on the hill, and you found a condition, if you release it, it'll roll downhill. So that's what you're looking for, is how to get it up on the incline and let the reaction proceed to roll downhill. And so that's the essence of thermodynamics. And there are connections between equilibrium and kinetics, even in the thermodynamics. Now, just a final historical note, thermodynamics is very young field as compared to kinetics and equilibrium, in that it evolved out of the Industrial Revolution for a need to study the steam engine and its behavior and to improve the efficiency of the steam engine. So we'll be looking at some of those efficiency factors and how to improve the feasibility of process. How do we measure rates of reaction, or describing the concept of rates of reaction? Of course, in chemistry, we find ourselves applying the idea of the term speed or rate, which means a change in some quantity as a function of time. In the world of chemistry, of course, as I mentioned earlier, rate of reaction has to deal with, or proportional to, or be defined by a change in concentration terms. Usually molar concentration terms over a change in time. And we've learned that concentration is molar, and molar is moles over liters. You'll see it moles per liter in symbolic form like that. So if we apply this idea, moles per liter, to this expression, our units of rate can be molar per liter, molar per second, something like that. That's the time frame in seconds if you want to do that. Or mole per liter over seconds. And then this translates into moles over liter dot seconds. So it's just invert the denominator and multiply back through the numerator. And you will see this used, as well as molar per second. Now, these are sometimes written in the negative exponent format, molar dot seconds to the minus 1, like that. So it just indicates that seconds is a reciprocal unit there. And if you have moles per liter seconds, it's the same thing as mole dot liters to the minus 1 dot seconds to the minus 1. And you will see these in different problems. If you look in the handout that I gave you, might look at across the top of those tables in there, and you might see something of that nature and how it is presented, because it's important that you be able to recognize the units and translate that into, oh, I got to do this in this problem. So that's your first step in understanding and describing rates of reaction. Now, in the measurement of rates of reaction, I want to make a note here. Really is dependent on the observer's ability to measure changes in concentration. And well, I'll go ahead and put it as a function of time. Given a reaction that might be in a container, this is going to give off signals that relate to concentration. I call them simply concentration signals. And in your development and understanding of this, it is important to understand, well, what can detect these concentration signals? What instruments, that is, i.e., instrumental methods. What instrumental methods are used to define concentration? And if you stop and think about it, you'll be able to mention one you're working with in lab right now. So instrumental methods might be pH detection. If you can measure the differences in pH as you go through a reaction, that's what the demonstration will show you, a change in pH as a function of time. And we can translate that into concentration terms and divide it by time and get a rate number. Also, you can measure rates of reaction in terms of electromagnetic radiation, light, spectrophotometry. Spectrophotometry typically is a UV visible range of measurement, and the reaction may start with a color and then fade over time. The change in time is proportional to that function of concentration, and from that you can get a rate. So what I'm not asking you to learn how to do spectrophotometry. I'm just saying that there are different ways to deal with concentration terms, and these are the two primaries. There are spectroscopy, which is different than this. Spectroscopy is things like infrared, and they give you a different pattern about a compound than spectrophotometry gives you. Infrared is a different range of electromagnetic radiation. Well, if you study the manual on how to use the instrument and apply it to determining concentrations, yeah, okay, you can get a concentration change as a function of time, and that's a rate. And so it's a matter of what you can measure and then apply it to the definition of rate. Energy changes. Usually a change in temperature as a function of time, you'll find is a good measurement. So you start out and you're just measuring temperature changes and you time it. How long does it take to go from 100 degrees down to room temperature? So that's a rate, okay? And you might have a concentration change related to that, okay? Now, one very important topic here is what do we relate in a chemical reaction to this concentration measurement issue is what is very, very important. You can relate either side of the equation, something out of the reactant side or something out of the product side. And I'm going to show you the reaction that I'm going to demonstrate in a little bit. Is it's called salicylases of T-butyl halide. Now, what we're talking about is finding a way to measure a change in concentration of a reaction. I'm just using this as an example in the demo, and you will see this again in the lab. Well, this compound called T-butyl halides, and you recall group 7 on the periodic chart, fluoride, chloride, bromide, iodide are your halogens, and so this is an organic compound with one of those halogens on it. And a T-butyl group looks like this, just for your information. As a science teacher, I'm obligated to share things like this with you. And generally, the halides are represented by an X. And you might note X is equal to a fluoride or a chloride or a bromide or an iodide. Now, we have some chloride and bromide in our collection over here, and that's the ones you'll work with. But if I take, say, the chloride and put it where the X is, I will have a structure that looks like this. Okay? And if I drop this compound into a 50-50 isopropyl alcohol water solution. The IPA is there to improve solubility of the compound. In the water by itself, this compound is too organic and does not dissolve, but if you make a binary solvent of a miscible solvent in water, it will dissolve, and you'll see how that works. So I put H2O and IPA over the reaction right there, okay? The outcome of this is that the hydroxide from the water will hook up where the chloride is, and the chloride will hook up with the other hydrogen from water, and you'll have this structure. That will be the essential outcome of it. Now, there's a mechanism it goes with, and we'll deal with that when we get to the lab demonstrations and what have you. Now, the question is, you want to develop study the kinetics of that reaction. How are you going to do it? Well, what did I tell you was the principal method as for the observer? Measuring a change in concentration of something out of that reaction. Yes? Main concentration over time, because rate, as you remember, is a change in molar concentration over change in time. So that's our objective. But if you look at this, there are a bunch of compounds in there. So which compound can you use? Well, if you have an instrument that will detect how this concentration changes, then use it. If you have an instrument that can detect this, fine. It's a reactant. What's it going to do? You can expect it to go down in concentration, and you can apply the rate that way. Or if you can measure the water reaction or the IPA effect or this compound or HCl. This is one of the 6 strong acids. And how do we measure acids? Anybody remember their lab work? pH, you bet. Absolutely. So now I have a mechanism by which I can observe this reaction. Some reactions you'll be measuring disappearance or changes in pH over here. Or this compound may have a color, and then as it changes into something on the product side, that color goes away. And that says, okay, the time it takes to go away means that's how fast this one on the right's forming. So I'm trying to give you I don't know, kind of a practical perspective on when we talk about studying rates of reaction. It's not just this reaction. It's any reaction. What you're looking for is some way to detect how one of the components of that reaction changes over time. Once you develop that, however instrument you use, whatever instrument you use, then you can logically define the kinetics of a chemical reaction. And I'll demonstrate this in just a few minutes. I want to go on and get the introductions out of the way. Then we'll do a demonstration to show you this. What affects the rate of any chemical reaction? There are 5 factors. You change one or more of these factors, you will change the rate of the chemical reaction. And I've put together a little acronym, C-A-N-T-C. Can't see. It's a great little acronym, fits real well. It's not a principle, it's not a law, it's an acronym to help you remember the factors that go into changing a reaction. C stands for concentration. Of the components. Now, we've talked earlier about measuring concentration changes. Surface area, and just A stands for area. N is nature. That is your chemistry of the molecule or chemical structure. You change one of the elements, like we just showed you, T-butyl chloride. Well, what if I got a T-butyl bromide? Well, you change the structure. That's what we're talking about, nature. And it does affect the rate of reaction. Temperature effects, actually it's energy effects, but temperature is what you'll be measuring. There are things that you'll learn about shortly called activation energy. All reactions have what is referred to as an activation energy. You have reactants that have to be energy-wise promoted to a point higher than where the reactants are, energy content. And at that point, the magic takes place and products are produced. If it doesn't reach that point, nothing happens. So that's a principle that you will hopefully appreciate when we get into studying temperature and energy effect. And then finally, a thing called catalyst. This is a compound which changes the rate of reaction, but yet is not consumed by the reaction. Now, I like to divide catalyst into two categories: accelerators and decelerators. You have some catalysts, and they're chemical in nature, that will speed a reaction up because you put it into the reaction mix. And then there are some which you will slow a reaction down if you add that into the reaction mix. And so those are deliberately made. Example, there are additives for your radiator fluid, your coolant, that slow corrosion. And then there are additives that you will put into reactions to speed them up, to make them go faster. Some medicinal medicines that are made have catalyst in them to make it work faster than it would normally. In the efforts that we're about to expend, we're going to teach you about concentration effects. The whole book is about nature more than anything, and we'll talk about catalytic effects. The issue on catalyst will be minimal in that we'll talk to you about how it affects what we call activation energy, raises or lowers activation energy. And surface area is also minimal in that if you increase surface area, you increase rate of reaction, and we'll be only descriptive in that. In this context, if you tried to start a campfire, what would you use? A log with high surface area, with a low surface area to light, or kindling to light the fire, obviously the kindling. So that's increasing surface area, and generally it speeds up the reaction. Beyond that, we're not going to get into the calculus of surface area, rates of reaction, and so forth. But just to give you a cross-section of what our interests are is in concentration, nature, and temperature is what we're really focusing on. Okay. Now, how do we apply these rate factors? And what we'll come up with is a mathematical expression. That's what the objective of this section is to come up with a mathematical expression that defines the rate of a reaction or system that you are studying. So that's the whole crux of doing the studies in kinetics, to come up with this equation that applies to the reaction of interest. And these equations, or these mathematical expressions, are called rate laws. Rate laws are mathematical expressions defined in terms of the rate factors. That is, rate is proportional to a function of a rate factor that we just talked about, can't see. Rate's proportional to a function of concentration. So if you change the concentration, something's going to happen. Or may not happen, then we'll see. Rate is a function of surface area. Rate as a function of changing the structure. Rate as a function of changing the energy conditions. Rate as a function of changing catalyst. And you can write an equation. I'm going to show you how. That's why we're here, is to learn how to take a reaction, apply concentration measurements, and come out with this rate law that defines the behavior, rate, speed of a reaction, and that you can apply in all conditions.